Hi, I'm Viroshan Ryan, and this is my EECS 376 application video. All right, so today we're going to be talking about Turing reductions. So we say A is Turing reducible to B if, given some decider for B, we can also decide A. So suppose that A is Turing reducible to B. Then if B is decidable, A is also decidable. That just comes from the definition of Turing reducible. And then by the contrapositive, if A is undecidable, then B is also undecidable. All right, so let's go to an example of how we can use this to show decidability or undecidability. So let T equals the set of three strings: football, basketball, hockey. And now LT be the language of all machines M, such that M accepts all inputs in T, and it loops on all of them. So basically, it accepts if the input is football, basketball, or hockey, and for everything else, it loops. So we're going to show that LT is undecidable using a Turing reduction. So we're going to say we have a Turing machine. We're going to construct it called S that decides L accept. And we're going to say we have a black box decider D that decides LT. And black box decider just means we can just trust that whatever value it gives is true. It can compute it. So basically, we want to show that if D works, then S also must work. So we have these two bottom steps for this construction of S. So let's talk it through real quick. If D of M prime accepts, accept, otherwise reject. So basically, S just does whatever D does, given some machine M prime. So basically, we want to construct M prime such that D accepts only if M accepts input X. Otherwise, we want to say it's going to reject it. And then if we do that, we can show that if D decides LT, then S must decide L accept. And then we can use the undecidability rule. So let's construct M prime now. So construct M prime as follows. M prime equals on input W. We're going to say if W is not in T, meaning it's not one of these three strings, we're going to loop. Then we're going to run M on input X. Again, this M is just the input to S itself. If M of X accepts, accept. Otherwise, reject. All right. So let's talk about why this shows the Turing reducibility. So M prime loops on inputs other than T, elements of T, right? And it accepts if the input is in T and M of X accepts. All right, so now let's say M of X accepts. What does this mean? This means that M prime accepts elements of T and loops on everything else. All right, which means it is part of LT, right? So this means D of M prime accepts, right? Which means that S accepts. Okay, so if M accepts X, then S accepts MX. So we're good so far. That fits the L accept criteria, right? So let's say does not accept. M of X does not accept, right? That means that M prime loops on that's not in T, right? And otherwise it rejects. Well, that doesn't fit this criteria for LT, which means M prime is not in LT. And since D is a black box decider, that's gonna reject, right? And if D of M prime accepts, accept, otherwise reject. So this means S rejects. Okay, so if M of X accepts, then S accepts. And if M of X does not accept, then S does not accept. So basically S decides I'll accept, right? And it only decides I'll accept if D decides LT. Well, we know that L accept is undecidable, right? This is our Turing reducibility statement. So we know that this is undecidable. Therefore, LT must also be undecidable. So we're able to do this using this construction of some machine and saying, if LT is decidable, then L accept must also be decidable. But since L accept is undecidable, we already know that LT must be undecidable. That was just a quick introduction to Turing reductions.